Okay, let's see. Is it gonna work? Oh, I need to probably change this, don't I? Why was it working earlier, though? That's so weird. Oh, oh, okay, never mind. It still is working. Okay, and then let's test chat real quick, see if it works this time. Test. Okay. And over here. Yep. Cool, cool, cool. And then good there. And I guess restream will show me the CUDA thing. Okay, cool. And then let's make sure that is up. Very good, very good. $720. Okay, yeah, I think that's fine. Should be good. Hopefully, anyways. And then yeah, let's get Vim going. Do some more of that. Hmm. What's the other? Okay. Let's close that guy. Yes, I've been bouncing around between Vim and PyCharm and VS Code and Cursor because I am now re-rigging my whole toolchain. But I think I'll probably either take notes or keep fiddling with this LSP config to see if I can get it like behaving the way I want it to. Because it ain't easy, bro. Vim is too hard for me. Or maybe it's lazy Vim that's too hard for me, but and it goes there. You can hide text. Oh, I guess I actually will put some text on the screen. Cause I need to advertise, bro. Where did it go? Is it not gonna work? In. Hmm. Ha, there we go. I guess now I can grab it. Cool, 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 cool. And then I can rotate it like that. And then that should work, maybe, in theory. Okay, so in theory, then I have the chat up, then I have them up. Oh, I guess I can just undock the chat, right? So I can just do this, and I can pull that over here and be able to watch it. Very nice, very nice. Okay, cool, cool, cool. Oh yeah, I should check in with pieces because I thought it would be real cool. Okay, so what do I want to be? What am I okay with?
The channel if you have filled the form, and if you haven't filled the form for this cohort, you won't be added to the private channel, but it's fine. You'll still have the access to these sessions, and once the cohort is complete, you'll have the access to assignments as well. So yep, nothing much to worry about. I'll say. So yep. Okay, so hello everyone. Welcome to week one again for this non-kickoffish session of mini cohorts by birds. And this week is about introduction to concurrency. We have released pre-reads for this particular topic as well, and we have given some. So we'll be giving some refresher and overview of those topics. So yeah. But first, I'd like you to meet John. So if you have been attending my sessions for a while, you'll know I every time I have some session, I just say meet John. So John is the go-to person that I say because John Doe is unknown. So yeah, yeah. So I would like you to meet John, and John is Kuda Land's first postman. But his job is not exactly easy. Like it's a pretty hectic job, more than ours. So uh, each day a new mail comes in, and one by one, John has to sort them out by places. And once a pile is completed, he takes it and delivers it to that respective places, and the process repeats again and again and again. Now, this is tiring and exhausting. So at the end of the day, John was also tired and exhausted. He knew he needs a solution. So he could have done the Saitama routine of 100 push-ups, 100 sit-ups, and built up his endurance, but sometimes that would give in as well. But yeah, one day he was just surfing YouTube, and John came across this video on concurrency. And after watching that, John was very hyped up because he found a solution to his problems. But what was the solution? So what he did was he went and bought some land in Kudaland and started a facility, and he called it post office. Now each post office had a head post, and since this was the first post office, John was the head post. And each day, head post would assign some task to each of the worker that was in that facility. Now each of these workers would execute their task based on some instruction that usually the head post would provide them. So that would be like sort these mails out, some would deliver them, etc. Slowly and steadily, John opened various post offices across the globe, and this is how post offices got famous. So this was a really bad story, but yeah, why does this matter? So story aside, this is sort of how concurrent execution works as well. Now you can think of that this task of postal delivery as process, and instructions to the workers are well instructions. So that's one thing, and workers executing these tasks and instructions are basically threads. So let's understand them more concretely. But yeah, so this is what we'll be discussing. We'll be starting by discussion on what processes and threads are. We'll understand what a program is, how a program is executed, what are threads, and what are processes. We'll then dive into what time slices are, what hardware and software threads are, and understanding what concurrency exactly is. So yeah, if you have any questions in the sessions, feel free to type it in the chat, or unmute yourself and just ask out what you wanted to know. So yeah, processes and threads. So let's try to understand what are we exactly executing. So if you're just viewing this meet right now, you are actually executing a task. You are having a task where some tab is opened up, this video is rendering, some network interaction is going on as well, just to make this meet, just to enable this meet for everyone, right? So some task is still going on your on your machine. So let's back down a bit and go to some simpler applications. What are we exactly executing? So it could be a Python script, right? So if you say create a Python script of addition of two lists, or number addition of each and every element of two lists. So that could be a Python script. Addition of two numbers that you input, that could be a Python script. Doesn't matter what the complexity is, you can execute a Python script. Or it could be an application. You can use Word, you can use MS Paint, or just open up this browser. It could be an application as well. So everything that, regardless of what you are executing, all that is happening is a set of instruction is being executed, right? So doesn't matter what you're executing, it is essentially just a series of instructions. Now, this series of instructions is what you call a program, and this is what your machine executes. So when a program is executed, its instructions are loaded on a RAM, and they're allocated some resources required for successful execution of that program. Now, these resources could be network, security controls, etc., right? Or memory or anything, basically. So yeah, so this program in execution is called process. So program could be an application, a script, or anything. But when it is being executed, it becomes a. So let's say we have a Python script that is being executed. This Python script, as I discussed before, is a program. Now, once you start when you execute it, the script is first converted into something called as a bytecode, and these will have the set of instructions that are meant to be executed, right? So in this case, it could be like, okay, get number one, get number two, add the numbers, display the result. It's much more complicated to read, but I have simplified it a lot over here, so just so it's human readable. So yeah, these instructions during execution are loaded onto a RAM and allocated resources for their execution. And they're loaded in a queue just for information's sake. And this program in execution, as we discussed before, is called a process. And the instructions, all these instructions that are being executed collectively are called a unit of execution. Now, each of these instructions is going to be executed by something known as a thread. One of the resources that is allocated during the execution is called a core. And this is the execution engine. This is where the execution of thread happens. So if a thread says, I'll execute this particular instructions, core is the one that is going to execute that thread. Now, a process can have one or more threads. If there is, say, like just one thread allocated to this process, then all those four instructions would be executed one by this single thread. This is the sort of sequential execution that usually happens on single core. But um, okay, so yeah, so that's how a Python script in a very base environment would look like. But that's not exactly how things happen with us, right? Like you might have Discord open up in your background. You might have File Explorer opened in your background. You might have Google Chrome opened right now and you're viewing this meet, or some other tabs might be opened up as well. So there are a lot of processes and lot of applications that are being currently executed right now in your machine. So if let's say multiple threads can be simultaneously, or multiple processes can be simultaneously be running in parallel, then that is something that you call as true parallelism. So let's say you have four processes, or let's say 1,000 processes running, right? And all of these 1,000 processes are being executed in parallel. This is called true parallelism. But sadly, we are compute limited right now. So let's say I have a
For
dual core
now.
processor. So I only have two cores, and each core is capable of either running one, or usually, or in good cases, like two threads at max, right? But you have multiple processes running multiple threads, or waiting, at least waiting to be executed, right? So what happens is the operating system rapidly switches between all of these threads for execution. So operating system would say, okay, your priority is high. You're viewing this meet right now, so your priority is high. I'll execute you first for some amount of time. Then I'll halt and I'll start the execution of next thread. Then I'll run it for some time and then start. Yep, exactly, context switching.
Shit. Well, I'm gonna have to
So, and
rotate
this
back to
all
you.
switching happens so fast that it creates an illusion of simultaneous execution. And this is what we call as pseudo parallelism or concurrency. And what thread will run at what time it will run, this is all decided by something called as a scheduler. And if you are knee about it, you can search about round robin scheduling and learn about it. Heads up, we'll have one question on round robin scheduling in the assignment as well, so you should learn about that as well. So yeah, that is all decided by a CPU scheduler. We learn more about schedulers next week, but yeah, that's how uh, uh, which thread will run at what time it will run. It's all decided by how is priority decided. So it's also a part of algorithm if I remember correctly. But yeah, I'll let you know on that. and the duration for which it runs is called a time slice. So the amount of time for which the thread will run is called a time slice, and that's the next topic that we'll be discussing. So yeah, over to you, Shamiso, for time slices.
Thank you, Hera. Um, Next slide, please. Yeah. So let's say we have an operating system and we want to provide some sort of multiple activities, which is usually the case, for example, on our phone or laptop, where multiple things want to run at once. So we want these activities to be isolated. We don't want them to interfere with one another. For example, on your laptop, any program can read or write any file written by another program. So we also have time multiplexing, which is the ability to share a single resource, where if we have a single CPU, we're going to use that single CPU for one application for a while, then use it for another, and then maybe come back to the first application. So for time slicing, which is a way of ensuring isolation, we want to make sure processes can share a CPU, of which this can be done cooperatively, where if we have, for example, process A, it will do its stuff and then call yield and then return. So the kernel will check if there are no other processes running. And if that's the case, it will return back to process A. But if we have process B also running, when the call to yield happens in process A, the kernel will go to process B, and this goes on like a ping pong iteratively. Please go to the next slide, Henry. All right, so when we talk about software and hardware threads, software threads, which are also known as software supported threads, are managed by the operating system and represent the virtual execution units within a program. So these threads are created and managed at the software level and are independent of the underlying hardware. Software threads are typically implemented using programming languages and are scheduled by the operating system for execution on the available hardware threads. And then when I speak of hardware threads, which are also known as physical threads or hardware supported threads, these are managed by the CPU and represent the actual physical processing units within the processor. So these threads are created and managed at the hardware level and are typically associated with multi-core processors, of which each hardware thread is capable of executing its own set of instructions independently. So communication between hardware and software threads occurs through thread management mechanisms. So the operating system is responsible for scheduling and coordinating the execution of software threads on the available hardware threads. So this communication often involves context switching, where the state of a software thread is saved and restored when it is scheduled to run on a hardware thread. Additionally, synchronization mechanisms such as locks, semaphores, or even message passing can be used to facilitate communication and coordination between the different software threads running on the hardware threads. So yeah, I hope this was understandable. I'll have to hand over to Ankesh.
Yes, thank you, Caroline. So, hi everyone. Let's talk about concurrency now. Here on next slide. So, as promised in the last week's session, we will be using the pizza example. So, let us understand what is concurrency. Concurrency in operating systems refers to the ability of the OS to manage and execute multiple tasks or processes simultaneously. So, for example, like in the dominoes, right? So, somebody will be taking the order, somebody will be making the dough, somebody will be cutting the veggies for topping, somebody will be putting the base that's ready in the oven, and yeah, finally we will have the pizza. So these all tasks in the Domino's store or kitchen are happening simultaneously. So that is what concurrency looks like. Next slide. So what are the techniques by which concurrency happens? So these are the ones. So don't look at the images. These are not the actual ways how the CPU does these tasks. But let's, for example, understand what multitasking is. So multitasking involves the execution of multiple tasks by rapidly switching between them, as you can imagine, and each task gets a specific time slot, and the OS switches between them quickly, and it happens so quickly, it's so fast that we cannot even realize that, okay, there is some switching happening there. So it seems that it is running simultaneously. Uh, Again, like in the context of pizza making, you can see that the ability of the restaurant to, or the Domino's kitchen, to handle various types of activities at the same time. For, let's say, for example, employee might be taking orders over the phone, intermittently managing the cash register, and also coordinating with the kitchen staff about the order statuses and all that. So only one person is doing all of these different tasks. This is what multi-process. It relates to, like in the Domino's example, it can be seen as all of these multiple tasks done by different workers. They are kind of concurrently happening, and that is kind of an example of how multi-threading takes place. And again, multi-processing goes a step further, and here we are basically distributing multiple processes across multiple physical processors or cores, achieving parallel execution at a higher level. So we will look at these, like, so if you can think of it, multiprocessors would be like multiple locations of Domino stores, because that's equivalent to, let's say, having multiple CPUs, because we want to deliver orders in different locations, and we can't do that if we have just one store. So we have to have multiple stores to kind of give fast delivery, and without any like bad services, so that we need multiple locations. So that would be multiprocessing. We use multiple CPUs to do the same thing. Next slide. So why do we need concurrency? As you can imagine, there is a lot of
I'm sorry. I think we had a question.
okay. This one in the chat, right? Can any task be sent to a different processor? I think yes, it can be sent to a different processor. Like a task can be broken down into multiple subtasks, and those subtasks can run on different processors. We'll look at the example in the next slides. So yeah, why is concurrency needed, right? So let's look at these 4 reasons. First is resource utilization. So concurrency ensures that the CPU, memory, and all the other resources are used optimally. So without concurrency, a CPU might remain idle while waiting for the input-output operations to complete, leading to insufficient resource utilization. So this is one reason. Another is responsiveness. So concurrent systems are more responsive. So users can interact with multiple applications simultaneously, and the OS can switch between them quickly, providing a smoother user experience. Throughput. Concurrency increases the overall throughput of the system, and multiple tasks can progress simultaneously, allowing more work to be done in a given time slot. And real-time processing. So obviously, as discussed earlier, that it happens so fast that we cannot realize the switching of the tasks between the concurrent uh, processing. So that's why it's real time. and it ensures that processes can run without interruptions, delivering a seamless experience. Next slide. So, of course, I mean, there is so much happening. There is so many processes and threads running in concurrency, and there's like you can imagine, like we are the ones programming it. So there are definitely some pitfalls that we need to look after for, because they can be very serious. And I read in one of our resources that one of such programming errors had caused some like 4 deaths, and that is something very serious. And that's why we really need to avoid these pitfalls. So let's understand more about what these pitfalls are. Um, Next slide. Yeah. So race conditions. Yeah. You can see in the image that there is like these players racing to reach the first position. Similarly, in the CPU process, there are different tasks that are hungry for the same kind of time slot or same resources, and we can imagine this to be race conditions. So what are they? They occur when multiple threads or processes access shared resources simultaneously without proper synchronization. So in the absence of synchronization mechanisms, race conditions can lead to unpredictable behavior and data corruption. So this can result into data inconsistencies, application crashes, or even security vulnerabilities if the data is sensitive. And imagine that, for example, in the pizza Domino's example, right? So imagine if two workers are tasked with updating the same digital order status. So one is marking as the order is in the oven, and while the other marks it as ready for delivery. You know those Domino's trackers for delivery, right? So what if like there are two different statuses shown there? That will be very confusing. So depending on the timing of their updates, the system might end up with incorrect information, leading to a potential confusion about the order's actual status. And this is something as race conditions. Next slide. So we will understand what's happening in this figure, but I'm sure all of you know what a deadlock is. You have heard about it. So a deadlock arises when two or more processes or threads become unable to progress as they are mutually waiting for resources that are currently held by each other. So this situation can bring the entire system to a standstill, causing disruptions and frustrations for the users. So what's happening here? So process one is holding on to resource one at the same time, and at the same time it needs resource two to proceed with its operation. So process two, meanwhile, is holding on to resource two, and it requires resource one to continue with its work. So both these processes are waiting for each other to release the resource that the other one needs. So however, neither is willing to release its own resources and resource until it is acquired by the other. So as a result, both processes end up waiting indefinitely. And this kind of stalemate situation basically is what we know as deadlock. So going back to the Domino's example, suppose two kitchen staffs are assigned to prepare pizzas, and each need both the rolling pin and the sauce spoon to complete their task, for example. Very random example. But yeah, if one worker has the rolling pin and the other has sauce spoon, and they are both fighting for the same resources at the same time, this would be like a deadlock. And there are techniques to avoid this, but yeah, we'll go through those later. Next slide. So another pitfall that we need to avoid is priority inversion. So what is that? So priority inversion occurs when a lower priority task is temporarily holding a resource that a higher priority task needs. So this can lead to delays in execution for the higher priority task, which is completely unreasonable. So, and it also reduces the system efficiency and responsiveness. So let us understand what is happening in this figure to understand priority inversion in detail. So, so there are these two tasks or threads represented here with different priority levels. The lower priority task acquires a lock on a shared resource, as indicated by the lock arrow at the beginning of the lower green bar. The higher priority task then attempts to acquire a lock on the same resource, as shown in the figure. Since the lower priority task already holds the lock, the higher priority task must wait. This is indicated by the dashed line extending to the right from the lock arrow. And normally the higher priority task would expect to execute quickly because it's higher priority, and because it is blocked by the lower priority task, which is holding the lock, the execution is delayed. So this is the priority inversion. So it basically spans the time from when the higher priority task starts waiting for the lock to when the lower priority task releases the lock. So all this time between that is called the priority inversion. So this situation is described as unbounded because there is no limit on how long the higher priority task might have to wait. And let's say if a medium priority task, which is not shown here, would start executing, it would further delay the lower priority task from releasing the lock, so thereby extending the wait time even further. So this is completely, it should be definitely avoided. So yeah, after acquiring the lock, the higher priority task proceeds with the execution as shown in the diagram by the yellow bar. So priority inversion can lead to performance issues, especially in the real-time systems where high priority tasks are expected to execute and complete within strict timing constraints. And to mitigate this priority inversion, mechanisms like priority inheritance or priority ceiling are observed. Yeah, we'll learn about them later. Next slide. So another pitfall is resource starvation. As the name suggests, basically processes or threads are basically waiting for the resources. So let's understand what's happening in this example. So it occurs when some processes are unable to obtain the resources they need, leading to poor performance and responsiveness for those processes. And this can happen if the operating system does not manage resource allocation effectively, or if certain processes monopolize resources. So there are several processes shown here, each with a different priority level. So priority 5 being the lowest and priority 1 being the highest. So in this diagram, we can see that it indicates that there is a continuous arrival of new processes with lower priorities. So there is a process with priority 5 that is ready to be executed, but it keeps getting preempted by incoming processes with higher priorities. So priority 4, 3, and so on. And the circle with priority 1 in the purple square represents that a process is being currently executed. So the text here is just basically telling us that these are the priority numbers of these tasks, and how the lower priority tasks are basically just waiting continuously for the resources. So this explains us that starvation refers to a situation where a process or thread does not get required resources to proceed with its execution because other higher priority processes keep preempting this execution. So basically, this is starvation. And for example, if you recall our Domino's example, if one part of the process monopolizes a resource, other tasks may be indefinitely delayed. For example, if one worker uses only the oven continuously for large orders, let's say, then medium or small pizza orders will never be fulfilled, for example. So yeah, that would be resource starvation. Next slide. So how can these pitfalls be managed? So to effectively implement concurrency in operating systems, the programmers adhere to these solutions to avoid pitfalls. So what are those? Process isolation. This is basically that each process should have its own memory space and resources to prevent interference between different processes. And this isolation is critical to maintain system stability. The next one is synchronization. So concurrency introduces the possibility of data races and conflicts, as we have seen earlier. Synchronization mechanisms like locks, semaphores, and mutexes are used to coordinate access to shared resources and ensure data consistency. We will learn about all these concepts in the next sessions in detail, so don't worry about finding them foreign right now. Deadlock avoidance. So yeah, OS can implement algorithms to detect and avoid deadlock situations where processes are stuck waiting for resources indefinitely. So and this can hold the system. So we definitely need these algorithms. So, and fairness is the last way to manage concurrency. Though it should allocate CPU time fairly among processes to prevent any single process from monopolizing system resources, as we saw in the resource starvation pitfall. So yeah, next slide. This is how we manage concurrency. Now, lastly, let's understand what's the difference between concurrency and parallelism. Next slide. So yeah, I think earlier somebody was asking the question related to this. So yeah, so this is concurrency, right? So we can see, we understood that the CPU divides its time in, let's say, handling these two threads. And we can see that the green blocks and blue blocks are not happening simultaneously, but at the same time, these two threads are running simultaneously. So they are being processed in the same time, but they are still, there is no interference between these two threads, and this is what concurrency is. Next slide. But in parallelism, there would be different processors handling these different threads, and they are completely independent of each other, so they can run at the same time. So there is no interference between them because there are different processors used for them. So this is parallelism. And next slide. So yeah, in this slide, we can see that there are some executions that happen parallelly as well as concurrently. So this is an example of that. So you can see that thread 1 and thread 2 are running on CPU 1, and thread 3 and 4 are running on CPU 2. And like all these threads are running simultaneously, but because there are two processors used in this example. Now there is no interference between thread 1, thread 2, and thread 3, thread 4. So this is an example of parallel concurrent execution. Next slide. So to revise, we learned about processes and threads and time slices, and we also spoke about concurrency in this session, but we will go in detail about the different things that were mentioned in this session and how to handle concurrency, and all these topics we will be discussing in the next session. So multi-threading, multiprocessing, we will see them in details. We'll talk about semaphores and thread locks and queues and everything like that. Of course, you will get the resources on Monday. But yeah, this concludes today's session. If anybody has any questions, we are here to take them now. Next slide.
Yep. So next week would be much more practical. We'll have a hands-on on Python as well. I hope everyone is well versed with Python, right? I'm going to assume everyone is well versed with Python. So yeah, maybe. No, I mean some people like Rust, some people do Java. So yeah, just
Right.
in case.
Yeah. Mostly Python should be comfortable for everybody here. Yeah.
Or maybe Mojo. Like we can try out Mojo, but let's stay in Python. All right. So I'm going to switch off recording now, so we can have an open discussion.
Okay, well that was freaking peachy fine. Sorry, I was gonna work on them, but I got distracted setting up PyCharm because I am, like I mentioned, re-rigging my whole tool chain. So I am not only doing the hardest version, but I am also doing the easiest version in terms of configuration, i.e. PyCharm versus NeoVim. But PyCharm does not seem to be able to find my Git executable, which is kind of strange considering that it can pull the commits. Although it wants me to update to an older Git version, which is hopefully fine. I'm not sure. I guess we can downgrade. I guess that's fine. Maybe my Git is too new. Hopefully it doesn't break stuff. I don't know. We'll see. Well, yeah, unfortunately I was only like half listening, but all of that makes sense. I think I have like a somewhat decent understanding of maybe I need to close and reopen. Uh, oh wait, hold on. Yeah, I'm assuming I need to close and then reopen. Can it find my Git this time? That is the question. No notifications just yet. Just fine. Yeah. The AI assistant, I would like to try it out, but I don't want to spend, I don't know. I don't want to burn the week and I don't. Well, what the fuck? Okay, so I guess this is a known issue. Yeah, it's just gonna repeatedly do that, I guess. Just kind of annoying. Okay, and then in theory it should work on the next restart, but let's go ahead and exit and just see if we can get it working. At the moment, see if that'll do it by updating my Windows paths. Okay. Well, and I guess I should get ready for the thingy later on. I don't know if there's anybody listening, watching, etc., but come through the server, link in bio, etc., at around 6, so about 3 hours from now, and then we will do kind of a little kickoff outline. Here's the deal, kind of shindig thing, and we will see about if we are gonna get enough people to do a hackathon this weekend, because that'll be fun. All right, catch you later, friends.